Right, okay, so what I'm here to do is to try and talk a little bit about chemistry and STEM. And in particular, I'd like to talk about what chemistry is and how it connects to this concept of STEM. And I'd like to use some very simple experiments, very simple experiences to demonstrate to you that chemistry is actually all around us and it's a fundamental part of any interdisciplinary science approach. Okay? Now, what I'd like to start with is I'd just like to get you thinking about chemistry in your everyday life. So I think that you will agree that every time you are in the kitchen, every time you are preparing food, perhaps when you're cleaning the bathroom, okay, you are doing chemistry in some form or other. And so we need to ask, well, what is this chemistry business? Well, chemistry is about elements, it's about atoms, it's about molecules, and it's about compounds. And chemistry is studying and understanding how these different pieces come together to make the world around us, to make ourselves, but also to allow us to make new things, to create things. Chemistry is about transformation. So you buy your meat from the butcher's shop or the supermarket or wherever, and you transform it into a roast in the oven. You can smell the roast when you come into your house. What's cooking? This is going to be really tasty. What's happening here? Well, this is chemistry. This is chemistry alive. So, one of the first things that I'd like to look at, not that plastic bottle of water. I'm going to have to zoom in here, I think. If we think about chemistry and matter, okay. So obviously chemistry is dealing with solids, liquids, and gases, which are the normal phases that we come in contact with in everyday life. Okay? Everything okay? Yeah? And of course, if we think about solids, well, we have lots of solids around us, of course. Just as well the chair is solid, otherwise we couldn't sit on it. If we think about gases, we have the air, and we're breathing gases. We're breathing a mixture of oxygen and nitrogen and some other stuff, okay? If we think about liquids, though, liquids are a little bit different. They're somewhere in between. So in liquids, we have this thing where if I take this orange juice and this water, you can see all I've done is I've just made the orange juice diluted. However, now I don't know, I think, yeah, do I need to go really close there? Okay, you can see here I have two layers. Okay, so I've got water on the bottom and I've got petrol on the top. Now, what does that tell us? That tells us that the floor is slippy here. That tells us that there is something about the petrol and the water which makes the water and the petrol not want to stay together. Now, you may recognize this stuff. Just 2 seconds. It's the antiseptic from the medicine cabinet, okay? So this is the iodine. Now, what have I done? I've dropped the iodine solution into this mixture. Now, let's just see what happens here. See if it works. And give it a few seconds. Okay. Right, it's not magic, it's chemistry. But I think what you can see, now, I have to, is there something white here? Yeah, just use this behind it. Can you see that? Yeah? It's gone purple. And the brown stuff has disappeared. Yeah? Oh, magic. So what's happened here? Well, what's happened is that in your medicine cabinet, in your iodine solution, you have iodine. But iodine prefers to stay in petrol. But the iodine solution in your medicine cabinet does not contain petrol. It contains water. And they add something else called povidone to keep the iodine in solution. So when you mix it with the petrol, the iodine prefers to go into the petrol because it's happier there. Now, iodine is an interesting molecule. It's actually not made of balloons, but it's like two purple balloons joined together, okay? And in this type of molecule, one of the iodine atoms is giving or sharing an electron with the other one, okay? So like sharing together, okay? So they're sharing two electrons to make a bond, and this makes the purple iodine molecule. Now, let's take something which is a little bit more. Now, this might be a bit difficult to see because this is. I don't know whether you can get in there. I'm not sure. This is just salt. There it is, salt. Okay. So, sodium chloride. Sodium chloride, very, very familiar, and sodium chloride is made of two elements. So whereas iodine is an element on its own, sodium chloride, is made of two elements. It's made of sodium, it's made of chlorine. Now, sodium lives on one side of the periodic table, and chlorine lives at the other. But together, they make a very stable salt. Now, if we think about salt, yeah, it's a white solid. Now, I don't know whether I can get to do this. I have a conductivity meter here. Well, it's not really a meter. It's a probe. And of course, if I do this, well, this is the crystal. Does it conduct electricity? A little bit further. Is that okay? Yeah? It doesn't conduct electricity. Yeah? Now, why is that? Why is that? Why doesn't sodium chloride conduct electricity? Because the sodium gives an electron to the chlorine, and the chlorine keeps it. So what we have is like a lattice, and this just goes out to the edge of the crystal. Okay, so you've got chloride, sodium, chloride, on and on and on. Now, what happens when we add a little bit of water? So let's just see if we can do that. Okay, I'll just get rid of some of that. I'm just going to add some water here. Now, this is where I would do this on a very small scale. And what you can see is that, oh, not too close. I don't know whether you can see this. Is it lighting up? Is it lighting up? Yeah, because I can't see it from here. Yeah? Okay. Right, so why is it now conducting electricity? Well, it's conducting electricity because the water has broken up the sodium and the chloride, the sodium plus and the chloride minus, and they're now free to move. So when you pass an electric current through the water, the ions can move, okay? So this is solids, this is ionic solids, but of course we have other types of solids as well. Now, let me just check. Okay, so the title of this talk was lemons. It's about lemons. And so you may be able to see that I do actually have some lemons here. Okay. And one of the things about lemons is they contain vitamin C. Now, vitamin C is an extremely important molecule for us, okay, because vitamin C is involved in defending us against oxidation. It's an antioxidant, okay? Now, since we're talking about lemons, but I've got some iodine here, vitamin C also reacts with iodine. So let me just see if I can get this to work a little bit. Okay, now I'm just dropping that in, and let's see if I can get rid of the brown colour. Ah, there it is, it's gone. Okay, are you okay with this? Va bene, is it fine? Okay, so I'm just going to add a little bit of iodine, there we go, it's nice and brown, in it goes, swirl it around, and it disappears. Okay, so what's happened? Well, this is telling us about another really important part of chemistry, which is transformation. Because chemistry is about transforming things. And to transform things, you need to break things and make things. Yeah? Now, in chemistry, what that means is moving electrons around. It's electrons. It's all about electrons, okay? So, what I'm going to do is I'm going to see if I can actually get that to go backwards. Okay? Now, this may work. Maybe. Okay, so this is my vitamin C. With my iodine in it. You can see it's essentially lemon coloured. This is starch with some hydrogen peroxide, which is another disinfectant from the medicine cabinet. Now, this may work or it may not work. I don't do this. Oh, there we go. Et voila. Yeah? Okay. Now, why has it gone blue? Why has it gone blue? Well, it's gone blue because in my vitamin C, in my lemon juice, I've taken the iodine and I've made it invisible. I've turned it into something else. I've turned it into I-, iodide, which is no color, has no color, okay? When I add the hydrogen peroxide, which we also use as a disinfectant, I turn it back to iodine, yeah? But iodine reacts very, very strongly with starch, okay? And when it mixes with starch, it goes blue. So that's what's happening here. Okay, so this is the so-called iodine clock, although it was extremely quick. So chemistry is about electrons. It's about making stuff. It's about moving electrons around. Chemistry is also about modifying molecules. And one of the ways we can do this is we can use acids and bases. Now, lemons are famous for being acidic. Okay? So, what I've got here is, I've got, actually, sorry, I forget to come over. I don't think you can see it very well, but it's an extract of some flowers. Okay, I found the flowers outside, so you can do this very easily. But what happens is the lemon juice contains a lot of acid, citric acid, ascorbic acid, and some others as well. And I think you can see it's sort of like a purple. It's like a purpley colour. I've got some baking soda here. Let's just see if we can get this to, am I okay here? Yeah? Okay. Okay, so there it is, it's gone green. Let me just add a little bit of water to dilute that so we can see it. Okay. There you go. So this is the extract of the flowers with baking soda. Okay. Now what happens if I add some lemon juice? Let's just hope this works. Okay. I think you can see that it goes frothy, but it's turned color again. Okay. Now, if you've got really strong acid, it will go bright red. Okay, but acid juice is not so strong that we can't eat it. Okay, that's fantastic. So, we were talking about roasts, and we were talking about excuse me. We were talking about smelling roast meat. Okay. Well, what's the process involved in smelling roast meat? The process involved in smelling roast meat, I'm going to put that there. It takes a little while. Oh, good Lord, it's gone almost immediately. Okay. It's the process of diffusion. Diffusion is molecules moving around in a fluid. Okay. So in this case, the molecules, I've just put some ammonia, the ammonia solution at the bottom of the bottle, and the ammonia is diffusing up through the bottle, and you can see, can you see this? Actually, I'll bring it over so you can see it. Yeah? You can see this, that it's diffusing up the bottle and it's coloring this paper. Yeah? Okay, this is a very, very easy experiment to do. If you want to know, I'll tell you how to do it later. Okay, so that's ammonia. Ammonia smells of ammonia because it's a small molecule which escapes from the water solution. Okay, another common molecule that we have. Does anybody have a birthday here? Anybody got a birthday? Your birthday? No? Your birthday? No? No? Okay, well, it doesn't matter, but we can imagine someone has a birthday somewhere. Okay, right, so what I need to do is we need to extinguish the flames. And so how do we extinguish the flames? Well, this is lemon juice, okay? Nice big syringe. What am I going to do? I'm going to get the foam to, come on, extinguish the flame. Do it, do it, do it. Yes! There it goes. Okay, what's happening here? It's the carbon dioxide. Now, carbon dioxide is something which, if anyone's interested in global warming, it's one of the things which people talk about a lot. We breathe oxygen, we breathe out carbon dioxide. Okay, in this case, we have the acid reacting with the sodium bicarbonate to produce carbon dioxide. But to glow, to burn, the candle needs oxygen. Carbon dioxide fills the glass, and there's no more oxygen available. Okay, so this is the carbon dioxide. Okay, so this is fine. So we've got ammonia, we've got carbon dioxide. I'd like to show you this one. This is another gas which I'm going to make. Let's hopefully see. Oops, ciao. Let's see if this works. Okay. Now, this is hydrogen peroxide from the medicine cabinet. This is potassium iodide, and I've got some soap here. So let's see if this works. Okay. And this may take a little while. Okay, so you can see. Can you see there's a lot of bubbles sort of forming here? And it's sort of starting to, it's not doing very much actually. It should be a lot foamier. Okay. Okay. Right, so it's starting to produce oxygen. Okay. Okay, now it's going. Now it's starting to go. So what I'm going to do is I'm going to leave that for a few minutes and just let it fill the flask a little bit. Okay, hopefully. And we'll come back to that, and I'll see if I can do something with the oxygen. Okay. In the meantime, I've got now this one's a bit small, so you may have to zoom in on this one. I've got another gas, although this one I can't really do much with here because I don't have all of the equipment I need. Aluminium foil from the kitchen. Hydrochloric acid, copper sulfate, and then a mixture. Now, what I'd like to do, I'll bring this over. What I'd like to do is I'd just like to put these in here. I'd just like to show you what happens when we put, let's just see, is that doing anything? Yes, it is starting. Now, can you focus right in on this one, okay? Now, if you look carefully, you can see that this is actually producing a lot of bubbles very, very quickly. Oh, it's even smoking, okay? This one, the one in the middle, is not really doing very much at all. And the one over here is not doing too much, but it's producing some bubbles. Now, if I take this out, oh, look at that, wow. Wow, that's pretty spectacular, actually. Excuse me. Can you see that? No. Ha! I knew you'd say that somehow. No, it's not. But think about what it is. Because if you think about what is in the system, hydrochloric acid, aluminium, copper sulfate. It's the exchange of the aluminium with the copper, yeah? And that's what catalyzes the reaction, that's what gets the reaction going. So you saw how much hydrogen that was producing. Okay, right, okay, this is it's sort of getting there. Just remind me to look at that in a minute because otherwise I'm liable to forget that. Okay, so we've got various bits and pieces. Now, here, since we're talking about acids and we're talking about lemons, one of the classic or one of the common acids that you find in fruit is tartaric acid. And tartaric acid is very important, has a very important place in the history of chemistry, but I'll come back to that in a minute. What I wanted to show you is a reaction in which tartaric acid is involved in giving and taking electrons. Okay, so in here I have some Rochelle salt, which is tartaric acid salt. I've got some hydrogen peroxide, and I'm going to add a little bit of copper sulfate. Let's see if this works. Okay, oh, right, okay. Can you see this? No, it's starting to go. Let's see if this works. Starting to go. Maybe. Come on. Come on, up you go. These things they're not doing very well today. There we go. Excuse me. Okay, so this is supposedly the tartrate boomerang, but it doesn't look like it's going to do much. Can I ask for someone to get me some hot water, please? Can someone listening to me out the back? Backstage, Yerlan, can you get me some hot water? Just a cup of hot water. I'll come back to this. We'll come back to this one. Okay? No. Hot water. Yeah, okay. No, that's fine. Okay, so we'll come back to that one in a minute. So, but one of the, here it goes. Let's see if we can do this now. Where's my stick? my Bernie thing. Right, okay, so here we go. Okay. Oops. Right, ready? Let me just make sure that that's... Okay, yeah, that worked. Thank you. Okay, no, it's okay. What's happening there? What's happening there is that the tube is essentially full of oxygen. Okay, so when you don't have flame, when you have an ember, there is enough oxygen for the fire to start again, and that's what causes this rather nice effect. Very, very simple, and it's actually a nice way to catch the oxygen. Okay, so we've got the hot water. Okay, that's fine. It's not fine. It's no problem. Okay, so we've got the carbon dioxide. Okay, yeah. Okay, right. So it's back to birthday time, and okay. Now let's see if this actually works. Okay, so one of the things about lemons. Tell me something about lemons. Yeah. They're yellow. They're yellow. Okay. And what do they smell of? Yeah, bravo. Okay. Right. No, very, very good. Because the taste of the juice is actually... Exactly. It's got natural compounds. It's a compound called limonene, which is in the skin. Now, limonene is a hydrocarbon. Now, I don't know whether... Did you see that? I might have to do it again. It's very, very quick. No. I need... Did you see it spark? Yeah? Okay, because limonene is a hydrocarbon which is in vesicles in the skin of the lemon. Okay, fantastic. And just put it here, please. Okay, yeah, just put it down. Just put it down. It's okay. Thank you. Come on, you. Do the business. Okay, and the hydrocarbons are, of course, flammable. It's just like petrol, basically. And when you squeeze the lemon skin into the fire, it causes sparks because it burns. Okay. Now I'm just going to get rid of that for a minute. Okay. So that's limonene in the skin, but limonene has a very unusual property. I need a volunteer. Yeah? Actually, 2 volunteers. Yeah. If you want to come up, okay? It's okay. Maybe a little bit further forward. Okay, you're fine. Fine that. Okay. Right, now. Just 1 second. Stop. So the cameraman can see, okay? Just 1 second, okay? Excuse me. These are perfume testers, okay? Okay, right. It's not dangerous. This is stuff from the kitchen, okay? Right. I'm going to let you smell it, but don't say anything, okay? Can you smell it? Yeah? Ready? Yeah? What does it smell of? Lemon, fantastic. Okay, right, don't go away. This is another one. Ready? Curious, yeah? Seems like lemon too. That's interesting. What do you think? You don't have to agree with her. I don't speak Russian or Kazakh. Yeah. Okay. Yeah, like a pine tree. Okay, right, okay, no, fine. I was thinking, no, it hasn't worked. Okay, no, it's great, thank you very much. Because what I have is I have two types of limonene, okay? One smells of lemon, and the other one smells like pine trees, okay? So thank you very much for your help, okay? Now, what's the difference between these two types of limonene? Because they are literally the same molecule, except, can you hold your hands up? No, you need two hands, okay? Right, put your hands like that, okay? Now, what's the relationship between this hand and this hand? You can't superimpose your left on your right, can you? No? No. What's the relationship between the left and the right? It's a mirror. Yeah, it's a mirror image, okay? So what we have is we have two molecules of limonene that are mirror images of each other, okay? One smells of lemons, and the other sort of smells like pine trees. Now, for any mathematicians and geometricians in the audience, the reason for this is actually to do with the molecules and the way the molecules are arranged in space. So, how many colors do I have here? Four colors, okay? What's the shape? It's a tetrahedron, university student. Yeah, it's not a square, it's a tetrahedron, okay? So it's like a triangular pyramid type thing, yeah? Now notice, I've got 1, 2, 3, 4 different colors. Now, one of the properties of tetrahedra is that I can make two forms, okay? You see how they're like mirror images, but if I put them, if I put them like this, excuse me, if I put them like this, you can see that they don't superimpose, yeah? Okay? Now, what's happening in your nose, and there are loads and loads and loads of molecules that are like this, particularly in cooking, okay? But what's happening in your nose is able to tell the difference. Some people more than others, okay? Yeah, and it's not the only one. There are many other examples in the kitchen. Now, it looks like my tartrate boomerang reaction has decided not to boomerang. But anyway, oh well. I'll make a note of that one. Right, okay, so chemistry. It's about electrons, it's about making bonds, it's about breaking bonds, it's about making new things, okay? And sometimes the consequences of these are changing color, changing phase, changing state, what have you, okay? But one of the other important aspects of chemistry is, when we're studying molecules, is separating things. To purify things, to find out what they're like, to find out what they are, what they're made of, how maybe we can make them, okay? Now, this is a process which is called chromatography, which you may or may not have come across. I need to set this up, it will take a little while. What this involves is, it involves separating molecules in a very, very easy way. We're using their affinity for a particular thing. In this case, it's paper. And what we're doing is we are letting a flow of a solvent wash over the molecules so that they eventually separate. Now, we need to give that a few minutes because it does take a little bit of time. But in the meantime, since we're talking about electrons, we're talking about changing color, I'd like to bring your attention to this thing, because this is a rather unusual thing. In this pipette, I have some salt. Okay, what color is salt? White. Okay, white usually. Be careful what salt you buy. Okay, okay, yeah. Copper sulfate again. Okay, so what I'm going to do, if I can get up from this because my knees aren't that great, what I'm going to do is I'm going to drip some copper sulfate through this syringe. Okay, now, whoa. See what's happening here? Let's see what color it comes out. Okay, let's see what color it comes out. I'm going to put some copper sulfate in here just so that you can see it for comparison. Okay? Right, okay, so you can see that it's coming out green. So what is happening here? This is really, really quite a change in color. Okay? So what's happening there? Well, the copper in solution in water is blue. And it's blue because it's surrounded by water molecules. Okay? Now I'm just going to let this drip a little bit because I want to collect some. Okay, so let me just sort of see if you can imagine. So you have like the copper atom, and it's surrounded by water molecules. Now, what happens when I put it through here? There's a lot of salt, sodium chloride, and there's a very, very high concentration of sodium chloride. It's not the sodium, we don't care about the sodium, it's the Cl-, it's the chloride. And what that does is it moves the water molecules away, and it replaces the water molecules to give you a nice, well, look at this. I think you have to admit that this is really a rather beautiful green color. Yeah? That is beautiful. Emerald green color. Okay, not that I'm making emeralds, okay? Now, that's fine. That's fine. Let me just put that there. Need just a little bit of water. Oops, a bit too much. Let me just get rid of a little bit. Okay, now let's just see what happens. Just put it in there. Let's just see what happens. Can you see this okay against my t-shirt? See what happens when I take some of this green stuff and put it in the water. Can you see? It's gone blue. Magic. No. No, because what's happened is the water, there's so much water now that it's moved the chlorine. Okay? Yeah? So I could do this all day, but it's not much fun. Instead, let's see, I think this is the stuff, because it's written in Russian, so I'm okay, right. So this is ammonia, and this is with the. Okay, you see this one? So what have I done here? I've moved the water molecules and I've replaced them with ammonia. Okay, and that gives me this beautiful blue, dark blue color. Okay, right. So electrons, complexes. This is moving stuff around. Okay. Okay, that needs a little bit more time. Just give it a bit more time. Okay, so what I want to 5 minutes. Okay, right. I need a volunteer, someone who's strong. You've already been. No, you look too strong. You come on. So, okay, yeah. Both of you. Come on. And you, Vinny. Okay? Right. Do you study physics? Chemistry. Okay. Do you study physics? Astrophysics. Okay. So we've got Einstein and we've got someone who is not Einstein, like me. Okay? Right. What is this? It's a spring, okay? As in spring is sprung, the grass is risen. No, that's a terrible poem. What happens to springs when you... Sorry? Yeah, they deform, but if you don't put too much weight on them, what happens? They go back, yeah? What's the law? You're the astrophysicist. Hooke's law. Hooke's law, yeah, you remember Hooke's law? Right, okay, this is not a normal spring. Oh, these are not normal springs. I've broken them. So can I just ask you to hold that and hold that? Right, okay. Now, you don't have to pull, you just have to feel the force, okay? You don't have to pull. Let's see if this works. Can you feel it? Yeah. No! It's nothing. Right, do you know what's happening here?
Yes.
Okay, can you explain it to him?
In English or in Russian?
Tell him in Russian. However you want.
Когда нагревается, то молекулы более быстрее движутся.
Okay, whatever that means. Notice how it's still warm. Tell you what, just going to put it in here. Yeah, when it cools down, okay, when it cools down, it will go back to where it was, but when I heat it up, it contracts, okay? Now, have you ever come across this in everyday life? Oh, sorry. Have you ever come across this before? No? Okay, you may sit down and I will explain what's happening. No. No. It's nitinol, which is the memory metal. Yeah? And so what you've got is you've got this idea of phase change. Now phases, we talked about phases at the beginning, solid, liquid, gas. Okay? In this case, you have two types of solid, and they exist, they're stable at different temperatures. Okay, so there's one that's stable at hot temperatures, and there's one which is stable at colder temperatures. So when I stretch it, this is at cold temperature, okay? But if I heat it, it turns into the form which is stable at the hot temperature, and it stays like that. It needs energy to transform. Now, you're probably thinking, oh, this is really sort of high-tech and stuff, but if you've ever had any dental work where you need a brace, okay, that brace was probably made of nitinol because it applies a constant force with your body temperature, okay, and so your teeth straighten, yeah? So there's another example of phases, solid phases in different forms of solid phase in the kitchen. We have chocolate. Chocolate exists, the cocoa butter fats exist in different phases, and there is one type of chocolate which comes from Switzerland which actually feels cold when you bite it, and that's a phase change, okay? Right, so I'm sorry about this one. I've been practicing it all week and it just didn't work anyway. So, thank you very much for your attention.